Welcome to the third part of VCAA Specialist Maths 2021 exam papers. In this video, we will present exam paper 1, question 9. There are 3 parts in question 9, and each part has a few sections. Most students did well in section 1 of part A, while common errors in section 2 of part A include failing to justify the choice of sign for the path of the particle in the first quadrant. Section 1 of part B generally was answered well. In section 2 of part B, some students mistakenly gave the wrong point of collision as they confused the parameter t with the x value of the point of collision. In section 1 of part C, many students missed the steps or made algebra errors in their working. In section 2 of part C, many students found the question to be challenging and were unable to arrive at the correct answer.
Hello, Math Champions! I'm Dr. Chen. If you want to improve your math skills and understanding so that you gain confidence, enjoy math more, and get better results, click subscribe and hit the notification button so that you don't miss anything.
Welcome to this VCAA Specialist Maths exam paper series. In this video, we will present question 9 of exam 1 in 2021 paper. It is a pretty long short answer question. The question starts with 2 position vectors r of t and s of t. Both position vectors are relative to a fixed point O of particle A and particle B, respectively, for t is within a closed interval from 0 to c, where c is a positive real constant. There are 3 parts in this question. In part A, there are 2 sections, and section 1 is to show that the Cartesian equation of the path of particle A is x plus 1 or in parentheses squared over 16 plus 3y squared over 4 equals 1. Section 2 is to show that the Cartesian equation of the path of particle A in the first quadrant can be written as y equals square root 3 over 6 multiplies square root of the result of negative x squared minus 2x plus 15. In part B, there are 2 sections, and the first one is to show that the particle A and particle B will collide. Section 2 is to find the coordinates of the point of collision of the 2 particles. Part C also has 2 sections. Section 1 is to show the differentiation of the function equals square root of the result of negative x squared minus 2x plus 15. Based on the result of section 1, section 2 is to find the area bounded by the function square root 3 over 6 multiplies square root of the result of negative x squared minus 2x plus 15. The x-axis and the line x equals 1 and x equals 2 square root 3 minus 1, as shown in the diagram. It is also required to give answer in the form a square root 3 pi over b, where both a and b are positive integers. Now, let's answer the question by starting from part A. In section 1 of part A, based on the position vector A, we set the I component to x and j component to y accordingly. So, x equals negative 1 plus 4 cosine t, and y equals 2 sine t over square root 3, which can be written to cosine t equals x plus 1 all over 4, and sine t equals square root 3 times y over 2. Since the square of cosine t plus the square of sine t equals 1, we have the Cartesian equation x plus 1, or in parentheses squared over 16 plus 3y squared over 4 equals 1. Based on the Cartesian equation just being established from section 1, the equation is transformed to make y squared as our subject. After simplifying it, we have the expression y squared equals negative x squared minus 2x plus 15, or in parentheses over 12. Since the path is in the first quadrant, we have y equals square root 3 multiplies square root of the result of negative x squared minus 2x plus 15 all over 6. The first section of part B is to show that particles A and B will collide. In order to show that particles A and B collide, we equate both I and j components of position vectors of A and B and have two simultaneous equations, negative 1 plus 4 cosine t equals 3 sec t minus 1, and 2 sine t over square root 3 equals tangent t. The first equation gives cosine t equals plus or minus square root 3 over 2, and the second equation gives cosine t equals square root 3 over 2. So we may conclude that the particles A and B collide at t equals arc cosine of square root 3 over 2, which equals pi over 6 seconds. Alternatively, we may find their collision times through Cartesian equations. So in a similar manner, we establish the Cartesian equation for particle B by setting x equals 3 sec t minus 1 and y equals tangent t. Since the square of sec t minus the square of tangent t equals 1, we have the Cartesian equation for particle B, x plus 1 or in parentheses squared over 9 minus y squared equals 1. We have already known for particle A we have y squared equals negative x squared minus 2x plus 15 all over 12. And for particle B, we have y squared equals x plus 1 or in parentheses squared over 9 minus 1. If both particles collide, the equation negative x squared minus 2x plus 15 all over 12 equals x plus 1 or in parentheses squared over 9 minus 1 must have real solution. After being rearranged, it becomes a quadratic equation 7x squared plus 14x minus 77 equals 0. Since its discriminant is greater than 0, it has real solutions. At this stage, we may use the quadratic formula to calculate the x-coordinates of the collision point, which is 2 square root 3 minus 1. Then we substitute the x value back to the I component of both particles and check if they have the same time. So for particle A, we find cosine t equals square root 3 over 2. For particle B, we also find cosine t equals square root 3 over 2. Therefore, we may conclude that particles A and B collide. In summary, to prove both particles collide, we need to show that both of them appear at same position and time. Technically speaking, the first approach is more efficient than the alternative approach in this case. As for the second section of part B, since we have calculated that both particles collide at pi over 6 seconds from the first section, what we need to do now is to substitute pi over 6 to either of the position vectors. Hence, the x-coordinates equals negative 1 plus 4 times square root 3 over 2, which equals 2 square root 3 minus 1. In the similar manner, the y-coordinate equals 2 over square root 3 times 1 over 2. So the colliding coordinates is at 2 square root 3 minus 1 square root 3 over 3. Now let's differentiate the function in the first section of part C. To perform differentiation on such a function, we need to correctly apply the chain rule, the product rule, as well as the combination of both. In the meantime, as a student, you need to familiar with various formulas of calculus that stated in the given formula sheet. The details of differentiation are shown on the screen in a step-by-step manner. Finally, as it can be seen, the result of differentiation equals the square root of the result of negative x squared minus 2x plus 15. The second section of part C is to calculate the bounded area as shown in the diagram. So the area equals the integral from 1 to 2 square root 3 minus 1 of square root 3 over 6 multiplies square root of the result of negative x squared minus 2x plus 15 with respect to x. According to the given criteria in section 1 of part C, the area equals the function stated in section 1. Hence, the area equals square root 3 over 6 multiplies the sum of 8 multiplies arcsine of open brackets x plus 1 all over 4 close brackets plus x plus 1 all in parentheses multiplies square root of the result of negative x squared minus 2x plus 15 all over 2, all valued from 1 to 2 square root 3 minus 1. After the values of upper bound and the lower bound being substituted, it equals square root 3 over 6 multiplies open brackets 8 pi over 3 plus 2 square root 3 minus 8 pi over 6 minus 2 square root 3 close brackets, which is simplified to 2 square root 3 pi over 9.
If you enjoyed this video, please give it a thumbs up and subscribe to help me make more math content like this. I will see you in the next video.